The Laplace transform of a function y of t is defined as you see it. It's the integral of your function little y of t multiplied against an exponential e to the negative st. So the idea is you do this integral with plugging in whatever function you have. This is an integral with respect to t, so 0 and infinity get, quote, plugged in, unquote, for t, and in the end you're just left with the s. So in the end you end up with a function of s. So this process turns y of t into a new function, capital Y of s. And we were using the notation, the script L brackets y, to indicate take the Laplace transform of the function that's inside the brackets. And up to this point we had done three kinds of functions. A constant function, or just one, the Laplace transform came out to be the function 1 over s defined for positive s. Any power, t to the n, any power function, turned out to be a number n factorial over s to the n plus 1, again defined for positive s. And exponential functions, e to the at, ended up being 1 over s minus a, defined for s greater than a. So for s less than a, this is undefined. By the way, just something to note, the function y of t equals 1 is really a special case of t to the n, right? We could take n to be 0. T to the 0 would give us 1. And so it's a nice little check to make sure that when n equals 0 over in the Laplace transform side, that we get what we have figured out the Laplace transform for 1 is. And we do, right? If you put in a 0, 0 factorial is 1, and we'd have s to the 1 in the bottom. So we would get 1 over s. Actually, 1 also happens to be a special case of an exponential. If you put in a 0 for a, right, e to the 0t would be 1. So again, 1 is a special case of this entry. And if a is 0 over here, well, we would have 0, so we would have s greater than 0, and we would have 1 over s. So again, it matches up. So 1 is kind of redundant in two different ways here. It can be thought of as a special case of either of these two rows, and it agrees with both of those formulas. Now, in the rest of this video, we're simply going to add to this list. We're going to get sine and cosine. And the way we're going to do it is not by going back to the original definition, although we could do that, but that integral would be slightly painful. Doable, but painful. We're going to use the concept of complexification, which is this new process we've learned that can sometimes let us derive information about sines and cosines from information about exponentials via Euler's formula, which connects the two. So here I have that exponential rule, the Laplace transform of the exponential. And I'm going to remind you of Euler's formula says that e to the I omega t equals cosine omega t plus I times sine omega t. So in other words, cosine omega t is the real part of this complex exponential, and sine omega t is the imaginary part of this exponential. And so what we're going to do is we're going to take the Laplace transform of the complex exponential and then write that as a real part plus an imaginary part. And what we're going to conclude is that must mean that the real part that we get is the Laplace transform of cosine omega t, and the imaginary part that we get will be the Laplace transform of sine omega t. And that is legitimate. It turns out that that is true, that you can take real and imaginary parts and they will correspond in the Laplace transform. So we should be good, and this will be a quicker way to do this. So let's give it a try. So first of all, what is the Laplace transform of e to the I omega t? Well, we are going to assume, but again, if you think about how we got our exponential rule with real numbers up here, you'll realize that pretty much it's the same calculation. Nothing would be different. So in place of a, basically our a is I omega. So we would get 1 over s minus I omega. That would be the Laplace transform of the complex exponential. Okay, and then all we have to do now is break that up into a real and an imaginary part. Now I'll just do that in this lower space down here. 1 over s minus I omega. So as we've seen before, and as you remember from whenever the first time you encountered complex number division, the way to do this fraction, to do this division, is to multiply by the complex conjugate of the denominator in both the top and the bottom. So s plus I omega. So in the top, we get s plus I omega. And in the bottom, the whole point when you multiply a number times its complex conjugate is that the imaginary parts go away, the I parts cancel. You see that when you FOIL. You will be left with real parts, though. You'll be left with an s squared and a plus omega squared. And just you can think that through for yourself and see that when you FOIL, that's what you get. And that's the benefit of this approach, is that the bottom is just a real number, so I can distribute it. So I get s, and I'll write it here, but then I'll write it above as well. S over s squared plus omega squared plus I times omega over s squared plus omega squared. And so there I've plugged it into my diagram here. And so it turns out, and this is correct, that the Laplace transform of cosine of omega t is s over s squared plus omega squared. And the Laplace transform of sine omega t is omega over s squared plus omega squared. And so now these are two more rules that we can add to our list here. By the way, it kind of got lost in doing this complexification trick, but it turns out that that both of these are true for positive s. Okay, so s greater than 0 on both of those. This is just so that we're not writing anything that is incorrect, but this is not going to be a big deal for us for the most part. But yeah, it's true that the Laplace transform would only be for positive s in the case of cosine and sine. Okay.